Hello everyone. We'll start in a while. Let's more people join this live so that we're gonna start in two to 3 minutes. Please do let me know if my sound is okay and the video you are getting, everything is okay or not. Yeah, good evening everyone. Good evening. So only 8 members have joined till now. Please do share the live to your colleagues or your friends too, so that they can also join this live with the link. Already 7:31, so we'll start in 2 minutes. Yeah, good evening. Good evening, Aurangzeb. So, I think we should not make any delay today. We'll start now, and let the people join. They can continue. So, yeah. Um, in our last class, what we have seen, we have assigned the gravity loads, and we have created the model. Okay, we have done the moment release, right? So today I'll show you how to do the modal analysis of this structure. Okay, modal analysis of the structure. Now, what is modal analysis? In a simple language, how this structure is going to behave or going to deform under free vibration. Okay, this is what modal analysis is. And if you want to know more in depth, you can read any books of structural dynamics. Okay, you can read the knowledge, you can go to the ECSI knowledge base and you can read their articles too about the modal analysis. So from modal analysis, what we understand actually, the modal analysis tells us how the structure is going to behave under different vibrations. Okay, there might be earthquake load, there might be wind load, but what is the basic, uh, you can say, what will be the basic deformation, or what will be the basic response of that structure, whether it is going to take a rotational move, whether it is going to take a translational move. Okay, and there are some recommendations in the codes which those we have to follow for doing the modal analysis actually. So let's get started. Let me fix, I think in the video there are some glitches, right? Let me fix it. Give me a second. So let's not make a delay. We'll go for the modal analysis. Now, if you just see, I'll not get into the theoretical part of modal analysis because it's a vast topic, and you should actually, we all should read it, or we all should know the theoretical concept too. It is not yet fixed. Yeah, I guess it is fixed now. Okay, so to do the modal analysis, we'll go to E tabs first. Now in E tabs, what we have to understand, that this total modal analysis, we are not giving any load. Okay, any lateral load won't be there to move the structure. The structure will move under its free vibration. Okay, so we will consider free vibration means we are considering that the damping of the structure is tends to 0. Okay, damping means the internal friction between the members, among the members, right? So the internal friction in the members will be 0, we'll consider. So that is what free vibration is. So that means under free vibration, what is the ideal case? The first deformed shape of the structure should be translational. That means, suppose if it is your structure, if this is your structure, then no voice, someone's saying. Please do let me know if my voice is coming or not. Okay. So under free vibration, the first deformed shape which is going to create, it should be translational, means it should move under in any planned direction, like this. Suppose this is my structure, and in the first deformed shape should be like this, or should be like this, or should be in the other direction. Okay, so that means the first deformed shape should be like this. Okay, this is the ideal conditions actually. So I can write this deformed shape as mode 1. Now how the mode 2 will be? If you draw the mode 2, this is the ideal condition, but it may not be there in your structure, because all the structures you may not be having the proper distribution of stiffness and mass. Okay, so the second mode shape should be like this, means from here should be coming like this, which is my second mode, and this is also partially translational, so it will be my mode 2. What code says, I'm just drawing the code recommendation. And the third mode should be, see, it goes like this, then it goes like this, and it is coming again. That means here we are getting some rotation. So this is translation. This is also translation, maybe partially. And here we are getting rotation in the structure in this mode. Mode shapes means the deformed shapes. Okay, deformed shapes under free vibration. So this is my mode 3. Okay, so all these modes are depending on the eigenvalue. All of you have done in BTech the eigenvalue analysis. Okay, from the eigenvalue we can get the eigenvector, and this eigenvector, which is phi, this eigenvector represents these mode shapes, and eigenvalue means omega, the frequency. Okay, so this is the ideal condition. The first 3 modes should be like this. First mode translational, second mode also translational, it might be partially, and third mode should be rotational. But this ideal case you may not get in every structure. In critical structures, in irregular structures, you may not get this situation. Okay, so don't worry about it. Just try to make this first mode as translational. As our code said, we should try to create our first mode as translational. Now, as I am saying that trying to create this mode shape as translational, so let me discuss how we can create a mode shape translational and why the rotational mode used to be created. Okay, if there is any rotation, then what is the reason behind it? So let's not waste more time in it. Let's get into the E tabs. If you go to define, as it is, I am using E tabs 19 version 19. You can go to define load cases, and here you have modal load case. If you are using a old version, directly here only in the define option you will get. Let me cancel it. If you go to define, here itself you will be getting the modal case option. Okay, so for the higher version it is inside the load case. So go to define load cases. Yeah, gravity load should be there, man. Mr. DK Singh, for the modal analysis, gravity load should be there. Okay, the dead loads, the live load should be there. Okay, because the dead load and live load we are going to use for the seismic load calculation, right? Seismic weight calculation. So that seismic weight will be acted as the modal mass. I think you have studied that lumped mass we used to consider. If it is our structure at every story level, we used to consider M1, M2 like this, every story level, M3. So this mass is nothing but our seismic mass, or you can say seismic weight, and this seismic weight consists of 100% of dead load, 25% of live load if it is less than 3 or equal to 3, and 50% of live load if it is greater than 3. Okay, so this lumped mass should be considered in the modal case actually. So let me show you how we can consider it. Let's go to modal case and modify it. I'm getting a glitch in the software. Just give me a second. Define load cases, modal mass. You can modify it. Don't know what is the reason. Just give me 2 minutes. I'll close the software and I'll reopen it. I think there is a glitch in the software. Yeah, Mr. Arun, please send me your mail ID in the comment, not here in the comment, so that I can uh, send you the AutoCAD file. I have sent Mr. Singh already, and whoever need the AutoCAD file, please comment your email ID in the comment box, not here in the chat. Okay. And yeah, the alt move is off, Mr. Siddiqui sir. The alt move is already turned off. Let me check. I'm really sorry. Just give me 1 second. I'll check it again. Yes, yes, yes. The alt move is working. That's why it is. Now it will be fine. Actually, if you are using a third-party software for different works, that can make such issues. Okay. So let's go to define load cases and go to modal, modify. Again, it is yes. Now the load case name will be modal case. Okay, no problem. Now I'll tell you the application of these things in ETABS. Okay, the modal case will select as modal, the load case, and here we have two vectors. One is eigenvector, one is Ritz vector. Now let me just tell you when you should consider this eigenvector and when you should consider the Ritz vector. This eigenvector, whenever you have a simple structure, okay, suppose you have a simple structure like the one I have created in here as a demo model. Okay, so in this case you can use the eigenvector. Suppose this is my structure, a simple structure, and we have some floors. So in that case, to solve the modal case, you can use the eigenvector analysis. Okay, now suppose there are a tower at the top of your building, or maybe a small steel tower like this. Okay, and your building, suppose my building is like this, and this is the base. Now when a vibration you will give a when you give a vibration to this structure, what will happen? This bottom portion of the structure will move with a different frequency, and this top means the tower, the steel tower, will move with higher frequency. Okay, because this is very small, right, and compared to the structure below. So what will happen? It will move with a higher frequency like this, and this total structure will move with higher time period, means low frequency like this. Now what will happen here? The frequencies are not matching, right, here in the top and the bottom. The software is not capable of understanding these two behaviors. Now what will happen? It will calculate these frequencies separately, okay, the frequency of this model and this model, and it will give you a result which will be very absurd, because as we created this model together, we do not want separate values, right, or separate behavior, but it will be showing you a separate behavior. In that case, you will not get a mass participation. That means it will show that this small member, if you consider the total mass of the structure, and if you consider the movement of this particular member, what will happen? The mass of this particular structure is very less as compared to the mass of this structure below. Okay, so when the software is going to solve the total mass matrix, it will see that okay, this is the whole structure, and here only a small amount of mass is acting for the higher frequency. Okay, so in that case you will get a wrong value, or you can say a imperfect value or imperfect result if you use eigenvector. Now when you have such cases, you should always go with Ritz vector. What Ritz vector does, it will calculate the mass matrix of the structure separately, and when it combines the structure, it actually understands that this structure is belong to this structure below, but the mass which is having for this structure is not it's not enough for to compare with the structure below. So rather comparing it, what it does, it gives you the result for the the mean of the result. You can say the movement for this structure and the mass participation for this structure and the mass participation for this structure. It will calculate and give you a cumulative value. Okay, so in that case, in such cases, you should always go with the Ritz vector. Sometimes, again I am telling you, sometimes you may have some modeling error. Now what kind of modeling error? Suppose in any part of your structure, and this is a structure, suppose at any part of your structure, a small part of beam you have extended by mistake. A small part of beam you have extended by mistake, or maybe somewhere an extra node is there at the in here. Okay, you forgot to delete. Now what will happen when you are using eigenvector analysis? It will calculate the mass matrix for this small node also, and when it is going to compare it with the total model, you will see this small node is vibrating with a higher frequency as compared to the structure below. So it is not able, this eigenvector analysis is not able to differentiate between these two movements. Okay, so if you are getting mass participation very less, once try with Ritz vector analysis in ETABS, and I'm damn sure you will get a perfect result. And then also, if you are not getting a perfect result, that means there are a big problem in your structure, and you should check this out, or you should find this out. Okay. Okay, fine. Yeah, Structrex Private Limited. See, eigenvalue and Ritz value in details. Okay. The thing is, if I'm going to explain the eigenvalue analysis and Ritz value analysis, it is all about the theoretical concept, right? And at the first day itself, I told you guys that I'm not gonna explain the theoretical concepts here. And the mass matrix, whatever you're saying, mass matrix, all these things are there in the books. Okay, if you see a SDO system, single degree of freedom system, all these things are there in the books. But when you are going for the application, that application is not there in the book. The book is not telling you how to construct a high-rise structure. It will tell you, okay, this high-rise structure is going to behave like this, behave like that. But when you are creating a practical model or a practical project, that practical project will never match with the bookish, you can say the bookish concept you have get in your college days or in your suppose the study days. Okay, so the aim of my workshops are to tell you the applications, how you're gonna use these concepts to create a structure or to model a structure, to design it in practical field. Okay, and all the theories, I'm again telling you, there is no replacement of book. So before getting into this structural modeling, we all should read the structural dynamics. Okay, different books of structural dynamics there are. You can get any book, you can read from there, at least the basics. And already in our BTech days, we have already studied the eigenvalue analysis and all, the mass matrix, creation of the K value, the stiffness matrix, all these things, right? So let's go to ETABS. Here I have selected eigen vector because my structure is very simple structure, so I don't need Ritz. If you want, you can go with Ritz. There is no issue. Okay. So let's select eigen here. Here you have the geometrical non-linearity option, which is the P delta. I'll explain it later how P delta works. Here I'm going to take none. It's for this structure, and the maximum number of modes. Okay. So for the maximum number of modes, there are different concepts by different practicing engineers or in the books also. So the code says that at the last mode, suppose you have considered 5 number of modes, that means 5 number of different deformed shapes under free vibration. Okay, so at the last mode you should have at least 90% of mass participation. That means the mass matrix that you have created from this, at least 90% of the mass should be participated while creating the 5th mode or while creating the first 5 modes, these 5 modes. Okay, if it is not there in the 5th mode, if it is not 90%, what we should do? We should increase the number of modes. It might be 30 also. If you are getting 90% at the 30th number of mode, that is also okay. In some high-rise structures, you may have to go with 30 number of modes. Okay, so that is different concept. The main concept is we should have 90% of total mass participation. Now what is this mass? This mass is nothing but the seismic mass you have defined. Okay, that total mass, that means the seismic mass you have defined. So 90% of this the total mass should be participated for creating the last up to the last mode. Okay, now how many number of modes? There are few concepts. Suppose we have this structure, and this structure can move like this way, in the translational directions x and y. It can move and it can rotate also. So basically we have the three degree of freedoms here for the total structure, right? And number of stories, suppose we have 3 number of stories and 3 degree of freedoms. So 3 we should consider 9 number of modes like this. Okay, and some people says, okay, for every direction we have 6 degree of freedoms. Obviously here also we have rotation, here also we have rotation. So 6 multiplied by 9, sorry, 6 multiplied by 3, so 18 number of modes. So there are different concepts. Now what you should do, just take any value here. Here the default value is 12. Check whether this 12th number of mode is having 90% of mass participation or not. Okay, already I have explained what is modes. I think you have came late here. To just rewind the video, you'll see. Okay, so if there is this mass participation is not 90%, then you can increase the number of modes with, suppose, the 3 modes extra. You'll see with 15 number of modes. Okay, so this is a trial and error method, you can say. So for this, let's select 12 number of modes here for now. The minimum number of modes, obviously first at least one number of modes at least we want. Okay, and the cutoff frequency, frequent convergence of tolerance, whatever it is there, just keep it as it is. If you want to know more, I'll explain in a different lecture what are these things, because these things are already totally theoretical concepts. Okay, for now we will go with these values, whatever is there in the as a default. And here you can see the mass source is selected as mass source 1. The mass source is selected as mass source 1. Now from where did this one the software have taken? So for this, let's first click on OK. Click on OK here. If you go to define and mass source, you can see here the mass source 1 is defined and it is taken as the default mass source. So as we have only one mass source and we have taken the mass source 1 as the default, wherever you want the this mass source, it will be taken automatically. Now let's modify this mass source. Here mass source means the seismic mass. If you see IS 1893 2016 2002 whatever code, it says we should consider 100% of dead load, which includes the self weight also, 25% of live load when your live load is less than, my live load is less than or equal to 3 kilonewton, or 50% of live load when your live load is greater than 3 kilonewton. Okay, and you should not consider the roof load, the roof live load for seismic weight calculation. Now if you have any mechanical equipment at the top, okay, and if you are considering that mechanical load as live load, in that case you should consider the roof live load also. Okay, but in general cases we do not have, in residential structures we hardly have any mechanical elements at the top of the roof. So in that case we'll go with these options, which is 100% of dead load, 25% of live load if it is less than or equal to 3, and 50% of live load if it is greater than 3. So yeah, let's define it here. We'll not go with this element mass and additional mass, we'll go to specific load combination, load patterns. Okay, so this is my self weight, we'll take it as 100%, that means the multiplier will be 1. Click on add. We'll take the floor finish and click on add again. We'll take the masonry load also and add. So we have taken all the dead loads with 100%. It's multiplier, means 1 multiplier means the 100% of the load. And again we'll go with live load less than or equal to 3 and we'll make it 25%, that means 0.25 multiplier. And we do not have any live load which is greater than 3, right? So here it is, and we have, see, that's why we have created this roof live load separately, so that we can exclude this load here in the seismic mass. Okay, now we have include lateral mass and lump lateral mass at story level. Lump lateral mass nothing but already I have explained this lump mass. Okay, at every story level, for creating the seismic mass, it will consider it as a lumped mass. Means the total mass of the uh, building or structure will be concentrated at one point, which is our center of mass. Okay, so and this include vertical mass. This also you should consider whenever you are taking the vertical acceleration. So that means the vertical earthquake load. In the major seismic zones, zone 4, zone 5, we should go with the vertical mass also. So when you are defining a vertical earthquake load, you should also consider this one, include vertical mass. Okay, so in tall buildings you can see this vertical acceleration or vertical. Even if you are having a large, suppose this is your building and if you have a cantilever like this, so in that case, when the earthquake vibration hit your structure, you will get a major movement in this cantilever part also, so which is moving in up and down, that means the vertical direction. So in that case we should consider the include vertical mass option. Okay, so I'll show you how to consider the vertical load case also. For now we are not taking it because this is a very simple structure. In that case we do not need this. Click on OK now and OK. So we have defined the mass source. Now for modal analysis, we have defined the mass source, we have defined the modal case. Now one more important concept is there, which is called diaphragm. Diaphragm, actually the slab itself is called diaphragm. You see in the codes or in the books also, sometimes slab design also be called as diaphragm design. The slab itself is called diaphragm, but GM. Now why it is called as diaphragm? Okay, so if you see the definition, a basic definition of the diaphragm is nothing but a mathematical operator. Okay, this is an you can say the imaginary concept. Okay, this is an imaginary thing. If you see, this is my flow level, this is my flow level, right? And we have considered a lumped mass here, suppose mass 1, and the force, the lateral force is acting on this lumped mass. So this mass is at the floor level, right? This lumped mass at the floor level, and this lateral load, if you talk about the lateral load resisting members, here these columns or the shear wall, if you are having a shear wall, okay, these columns or this the shear wall is our lateral load or lateral load resisting members, right? So now if the lateral load is acting on this member, this lumped mass, that means at the floor level, from this floor level this force should be transferred to the corresponding lateral force resisting members. So what diaphragm does, diaphragm used to bind every single point at this flow level like this. To make it as a lumped mass, what it does, it binds every single point of this. It is, I am talking about, actually diaphragm has two types, which is rigid and semi-rigid. Sometimes you can call it as flexible diaphragm also, semi-rigid. I'll explain this too also. Just let me explain this. So what diaphragm does, diaphragm transfers this force which is coming in the lateral direction to the vertical members, which are our lateral force resisting members. Okay, now what is rigid diaphragm? Whenever you assign or you consider this diaphragm as, see, this diaphragm will be considered at the slab itself. That means in the real building, the slab that you are creating or you are constructing, that slab will act as a diaphragm. The slab will act as the transfer medium of the lateral force to the vertical members. Okay, but here in the mathematical software, you should have that mathematical software, actually what does, it does not understand that this slab is acting as a diaphragm or the diaphragm action. So what you have to do, in different other softwares like Strap, StatPro, they have different concepts. Okay, so in case of ETABS, what you have to do, you have to assign this diaphragm separately so that the slabs which you have modeled should act as a diaphragm or should give you this action. Now if you define this rigid diaphragm, what will happen? When the force is coming from this side, all the joints at this floor level, all the joints at why 90%, why not another value? Let me tell you. Okay, 1 second. So all the joints at this floor level will move together. Okay, all the joints at this floor level will move together in any direction, where from any direction, if it is coming from this direction, all these joints will move together at this in this direction. If you are considering a rigid diaphragm, that means it will consider this floor as a rigid body. Okay, so and in case of semi-rigid diaphragm, the force is to get distributed in every single point present on in this member, and this member is allowed to deform separately. All these joints are allowed to translate separately. Now when we should consider the rigid diaphragm, the basic concept is when you have a regular structure, regular shape of structure, suppose this rectangular structure, right? This is a regular structure. Whenever you are giving a load, there it tends to move together. All the points tends to move together. But if you have a structure like this, suppose this way, now this is a separate, if you see, this is a separate part, this is a separate part, right? And if the earthquake is coming from this side, this particular point may not move in this particular direction, or if the load is coming from this side, the behavior of this particular section, the behavior of this particular section may not match with the behavior of this middle section, the movements. So in that case, if you assign a rigid diaphragm, it will consider that all these points will move together, which is not the practical case. So in these cases, we should always go with semi-rigid diaphragm. But in every case, in every single case, if you consider semi-rigid diaphragm, there is nothing wrong. There is nothing wrong, because the semi-rigid diaphragm is the actual or proper behavior, you can say. So just to reduce the time that which will be consumed by the analysis process, okay, or just to make the process simple, what we used to do in the irregular structures, we used to provide rigid diaphragms, and in the irregular structures we used to provide this semi-rigid diaphragm. Again, depending on its length and width, if you see the ACI 318, there are even UBC 97. I don't know whether it is there in the UBC 97, but in ACI 318 it is there that depending on the length by width ratio also, the assignment of rigid and semi-rigid diaphragm depends. But there are very few explanation or very less explanation in our Indian code. So in that case, what we will do, we will consider this thumb rule, which is for regular structures you can go with rigid diaphragm, for irregular structures you can go with semi-rigid diaphragm. And if you want to go with semi-rigid diaphragm in every case, you are always welcome. There is nothing wrong. Okay, so let's define the diaphragm here. It is a simple building. So what I will do, I'll go to define, and here you can say the diaphragms D1. If you modify, and you can see this D1 diaphragm, you can change it to semi-rigid also. So for now I am going to assign the rigid diaphragm, click on OK, and I will create another diaphragm here, add new diaphragm D2 rigid. Okay, now why I have created this D2, I'll explain in a while. So click on OK. Now let's go to any plan view where you have the slabs. So this here we have the slabs. Is it correct? I think we should delete this slab, because this is our plinth level, so we should not have slabs here. Let me delete this, not this one, here slabs. Delete the floor slabs, we should not have the floor slabs. Okay, so let's go to the top level. Here also, if you want, that means the diaphragm should be there, because in this part also you can have some movement, right? So if you want to give diaphragm here at this level, what you can do means the floors are not there, but if you want to consider that here we have the floors and these floors will be transferring the loads to our vertical members. If you want to assume this, just to for the sake of assigning the lateral loads, so what you can do, you can go with the joint diaphragms. If you go to assign and joints, you can see we have diaphragms here, which are joint diaphragms. Okay, so we can provide the joint diaphragms here. So let's provide it here. Totally your wish. If you do not provide also, it's not an issue. So let's select all this. Let make sure that it is in one story. Go to assign, joint, and diaphragms, and let's select this one, D1. Apply. Here you can see it binds every single point present in this plane, and it has created the diaphragm. This diaphragm is also will be acting as we have created the rigid diaphragm. It will also act as the center of mass of your structure. Okay, now see, we have assigned diaphragm. Now what software will understand that we have slabs here. Okay, while solving the earthquake load or the lateral loads, what it will understand that we have slabs here, and this slab will transfer the lateral loads to the vertical members, which are the lateral force resisting member. Okay, but in practical case we do not have slabs, right? So let's go at the top and select again all the floors, and we go to assign shell. We can go to diaphragms and assign the first diaphragm, D1. Now we are assigning the shell as diaphragm, okay, because we are assigning the diaphragm in our slabs. Apply. Let's go to top, assign it again, D1. Now if you go at this level, now we have two different floors, right? Now in that case, if you assign a single diaphragm, what will happen? It will combine all, sorry, like not like this, it will combine all these points like this at this particular point. So is it possible to get the center of mass of this floor or this level in air or on air? It is not possible, right? That means we are considering that these two separate part of the building will move together, which is not the practical case. So what will happen in that case, if you have different separated levels, so separated models in one single plane, so what you should do, you should assign two different diaphragms to the different part of your building. Okay, it might be a multi-room, maybe you have different more stair rooms at the top. So in that case, every stair room should have different dead loads. Okay, so select this diaphragm, D1, select this diaphragm also, D2. Now we have defined that these two are allowed to behave separately, to move separately. This is the real case. Now click on close, and you can see the 3D, right? You can turn off this diaphragm actually. If you click on this show undeformed shape, here you can see the undeformed shape. Now let's save the structure, and let's click on run analysis. Now I have gotten a question that why 90%, why not other value? So when I have started this modal analysis part, what I have told that this is nothing but the basic behavior of the structure under free vibration, right? So when we are checking the basic vibration, or you can say the basic deformation under free vibration of the building, so every single deformation or every single mode are taking some amount of mass participation to create that mode shape. If you solve this the K matrix and mass matrix, and if you get the phi value, which is the eigenvector, okay, so here for different modal shapes we have different mass participation. Now suppose, let me just tell you, we have this amount of area, and someone have give you a work or a job to survey this area or survey the condition of the grass in this field. Okay, survey the condition of the grass of this field. Now if you check only this particular part, suppose this particular part, which is hardly 1 to 2% or maybe 3 to 4% of the total area, and if you create a report, okay, the condition of the grass in this field is okay, and you have not checked these parts, the rest of the areas, what will happen? There might be a damaged portion of the grass here. There might be an absurd behavior of the or absurd natural behavior of the soil here. If you are taking an example of a field, okay, so what you have to do, you have to examine at least 80 to 90% of the area, then only you can come up with a solution that yeah, the condition of the grass is something like this. In some parts we have some damaged grass, we should actually change it, or you can say we should make some you can say precautions to make it grow again, right? Or you can give some fertilizers there, the solutions to solve the problems, right? Now if you have read only 3 to 4% or suppose 50% of the problem, and you have left the other 50%, so there might be a chance that this 50% is more critical than the 50% you have examined. Okay, so in case of modal behavior also, this is the proper, or you can say this is the actual behavior of the structure under free vibration. When there is no lateral load, the structure is vibrating, the structure is allowed to vibrate by itself, as it don't have any you can say free vibration means it is not having any damping, so it is allowed to vibrate. Now when it is free to vibrate and it is vibrating in an absurd manner, then think when the earthquake vibration will come, and if you have given a extra vibration, external vibration, and it is vibrating in a very absurd manner, in that case what will happen during the major earthquakes or during the extreme earthquakes? So that's why the actual behavior, the basic behavior of the structure should be corrected before assigning the loads, before assigning the lateral loads. Okay, so to understand the actual behavior, understand the basic vibration of the you can say the free vibration of the structure, we should go with 90% of the mass participation. That means we have examined most of the behavior of the structure. Last mode means that up to this we will be examining, suppose up to this part we will be examining, which is the 90% of the total field. In simple language, this is the 90% of the total case. So if you have examined up to this, then you can come up with a final conclusion that okay, this area is bad, this area is good, and you can come up with some solutions to solve the issues, right? So, and in the code you can have the explanation about it, the actual theoretical explanation. Again I am saying I am not here to make you read the theories, I am not here to explain you the theoretical part. Okay, I am here to tell you the application part. To be very frank, I am here to tell you the application part. So whatever I will be explaining in terms of the application. Okay, so yeah, this is the thing, this is the actual case. So now if you see in eTabs, we have analyzed the structure, and if you go to tables, and if you go to analysis and results, structure output, and here you have the modal information, go to open this one, modal participating mass ratios, right click and show table, and here you can see we have assigned we have defined 12 number of modes. These are the time periods, means if there is a frequency, there is a vibration, there must be a time period. So here you have the time period in the descending manner, means the highest time period is at the top, and you have the mass participation values. Okay, now we have to understand the behavior of the structure from these mass participation values only. Okay, so let's understand this. See, in the first mode we have 85% mass participation. We have 85% mass participation in the ux direction, means x translational direction, and uy is totally 0. And if you see here in the rotational part, again we have very less, 0 rotation, this also. So the rotation we need to check is this one, the rz, because the vertical axis is z. If the structure is rotating, it will be rotating about the rz axis, z axis, right? So here you can see the 85% mass participation in the x direction. So what is the meaning of this? That means the 85% of the total mass, 85% of the total mass is participating here to move the structure or to create the deformed shape of the structure under free vibration. And as it is in the x direction, that means the structure is moving along the x direction. The structure is translating along the x direction. Again, in the second mode, this is a very simple structure. That's why you are getting such values. In case of critical structures, in case of irregular buildings, you may not get 85%. You hardly get 30%, 50% like that. Okay. You may not get couple modes also. Means here also 30%, here also 30%. That means the structure will not move in the proper translational direction. It will move diagonally. If you have mass participation in x and in y also, that means the structure, the plane direction, then it's not the actual x-axis. It is in the diagonal axis like this. Okay. So here we can understand that first mode, that the first deformed shape we are getting is purely translational, because most of the mass is participating in this particular direction itself. And if you see the second mode, again we are getting nearly 85%, 84, 0.848, right? So nearly 84%. So here also the most of the mass is participating here in the second mode. That means the second mode is, most of the part of the second mode or most of the deformed shape is going along the y direction, translating along the y direction. And if you see the third mode, there is no mass participation in the translational direction. That means the structure is not moving along the x or y direction. What I have told you in the ideal case, the third mode will be getting a rotational motion, right? Rotational movement. So if you see the rz here, you can see the participation in the rotation is 85%. That means in the third mode we are getting the rotation. So this is the ideal case here. Again, the next mode will be in the translational along x. See here. So this way it will be a repetitive process. Now, as we have got 85% at the first mode and second mode itself, at that the next modes you will be getting very less values. And you can see at the fifth mode itself, I guess, at the at the sixth mode itself, we have got 90% mass participation, total mass participation, not this one. This one is individual mass participation in particular direction, and this is means the cumulative value of all the mode participations along x direction. So you can see here we are getting 90%. That means in the sixth round itself, I have examined the 90% of the area or 90% of the behavior of the structure under free vibration. Okay, now we have the default value as 12. You can keep it. There is no problem if you keep extra modes. Not an issue. That means you are examining more. Not an issue, right? So if you want, you can delete the other modes also, because we already got 90% here in the sixth mode itself. There is another code provision, IS 1893 table number 6. If you see point number B, it says that we should have 65% mass participation in both plane directions. We should have 65% of mass participation in both plane directions for first 3 translational modes. Okay, for first 3 translational modes. Yes, Mr. Siddiqui sir is also right. Rigid diaphragm is also provided to calculate the center of mass. As I have told you already, the rigid diaphragm also represents the center of mass of the structure. So is there if there is a water tank on top of the staircase cap of roof slab, what to do there? Please do not model this water tank in ETABS itself or in the same model itself. Better you provide a load of the water load in the slab and the wall loads on the beams. Okay, just to consider the loading and design the water tank separately in another file or another model. Okay, so here if you see the third mode, so the code says that we should have 65% or more mass participation in the first three modes, which are in the translational directions, translational modes. Okay, so if you see here these first three modes, now these concepts, the actual concept is the first three modes dominating, in each plane direction. That means here this mode and this mode, these are the first three modes dominating in x direction, and this mode and this mode, you see these three modes are dominating in y direction. Okay, so some people used to consider the first three modes as these three modes, okay, 1 2 3, and consider this as the 65%, but the actual case is that in each plane direction the modes which are dominating, here the first mode is dominating in the x direction, the fourth mode is dominating in the x direction, and again the 12th mode is dominating in the x direction. So these are the first three modes for x direction, and again the second mode, the sixth mode, and the eighth mode, these are the first three modes dominating in the y direction. So the cumulative value of these modes should be 65%. That's what code says actually. So you can easily say the first mode itself we have 85%. So the cumulative value of these three modes will be more than 65%. So it is not an issue here. But in some practicing engineers used to consider this value, the cumulative mass participation of first three modes, as this one, the sum of ux and sum of uy, and they check whether these values are 65%. According to their concept, they also write, okay, if you see this concept, this is also right. But if you compare this as with our code, then it is wrong. Code says in each direction the dominating modes, okay, but the practicing engineer says that for the first three modes, the cumulative value of the mass participation should be 65%. Means according to them that in the third mode itself we should cover examining the 65% of the total area, or examining the 65% of the total behavior of the structure under free vibration. Okay, so they have one philosophy, the code has one philosophy. In most of the cases you will see, in some case on some irregular structures, in critical structures, you will see that it may not be, if you go with this theory, the theory of the code, that the modes which are dominating in each direction, the cumulative value of these three modes should be 65%. In some cases, or in if it is a critical structure, high rise structure or irregular structure, you may not get this 65% for the first three modes dominating in particular directions. Okay, so that's why most of the time we used to go with the philosophy of the practicing engineer, because whatever code we have, these codes are made by the practicing engineer themselves, okay, as per the practicing condition, as per the condition in a area, or you can say in a country. Okay, so the philosophy of this philosophy also correct in my opinion, and the philosophy which is written in the code, it is also correct. Okay, so because we are taking the participation, or you can say the behavior for every plane direction separately, we are seeing whether we have considered the total behavior or not, 65% behavior. Fine. And last mode I have already explained you, last mode we have got 90%. There are few more concepts, that it says, the code says that the difference between two translational modes should be 10%. Okay, The difference of time period between two translational modes. First two translational modes should be 10%. Okay, there if actually the main case is if it is not 10% or if it is less than 10%, there might be a case of modal superposition. That means simple thing I am saying you. Suppose this building is moving like this, and again there is another mode which is moving like this. Now if you combine these two behavior, what will happen? The structure may move like this in an absurd manner. So if there is a superposition of two modes, what will happen? The vibration will increase. Vibration of the structure will increase and you will get an absurd vibration of the structure. So to you can say overcome this problem or to avoid this modal superposition, you can check that whether the time period difference between the first two translational modes are 10% or not. But in some cases you may not get 10%. What to do? In that case, what to do? The one thing is you can increase the mass of the structure by providing higher section sizes, but it is not also economical. So code has its philosophy and the practicing part has their own philosophy. If it is not working out, you have to go with this only, and you have to make the structure or design the structure with that absurd behavior. That means you may get a higher reinforcement. Okay, you may get a higher reinforcement. Okay, so these things we'll see in the coming webinars. So when we will be solving a critical structure, maybe high rise structure or mid rise structure, then we may get this type of problem. Okay, so you can see these are the time periods, and for the time period you can write one formula which is actually empirical formula. It may not be correct always. The first time period which you are getting should be 0.1 10% of your number of modes or greater than this, should not be less than this. Okay, actually this formula is there in the IS 875 part 3 while analyzing the building for the dynamic wind load case. Okay, but in some practicing engineers, if you see, or in abroad also, they used to take this formula just for checking whether the first mode vibration or the first mode time period is equal or greater than this value, 10% of the number of levels, not number of story. Okay, number of levels. So yeah, is there any what? Okay, so now what we can do, we have got the idea of modal participation. Sum of means, if you see this means the cumulative value of extraction. This plus this give you the third one. You can see as these values are 0, you are getting the same value here, and again we have some value here, so you are getting a different value here, again in the same direction here. Okay, so this is our translational cumulative value, and if you go this side, you can see the rotational cumulative value. Okay, so our matter of concern is uy, ux, uz. Uz is also matter of concern when you are defining a vertical earthquake acceleration. Okay, when you are defining a vertical earthquake acceleration, in that case you will be having a mass participation in this particular area also. So then it is a matter of concern for you. Okay, so in this kind of simple structures, these things are not an issue at all. I can close this, and yeah, this is all about modal analysis, and I'll explain more. If you have any issue with the theoretical part, I am telling you, it is better you read any book. Okay, you read any book, and book is the best thing that can give you more knowledge, or that can give you proper knowledge about any concept. Read again and again, it will provide it, it will easily understand. But the application, it's not written in the books, right? Most of the books we have read or we are reading are not having that application part. So here I am just to tell you how I work or how I take these concepts to make an building design. Okay, so yeah, the modal analysis part is completed. In different structures, I'll show you if there is a rotation in the first mode itself, what we should do. Okay, so let's see the modal shapes now. For this, let's go to the top view, that means the terrace floor, roof floor, and I'll show you how it is deforming. Close it and go to roof floor. I think the all drag is again working. Yeah, there is a glitch in the software, I guess. Yeah, now you can see this is the top floor, and if you go to deform shape, show deform shape, and you click on the mode 1, and you just take this displacement resultant. I mean, it will show you the contour for if there is any displacement in x, y, and z, it will combine and it will show you the cumulative contour here. And check this one, draw contours on objects, click on apply. Now what you are seeing here, see, the blue color says the displacements here in this range. Okay, the range is kind of 44 to 48, I guess, or 48 to 52 mm. Okay, if you see here, it is there in the x direction, right? 0.49, and here I think e power minus 3, yeah, e power minus 10 power 3 is there, 10 power minus 3 is there, not like 52. 52 multiplied by e power 3 means 10 power 3 is the exponential unit actually, and you can see here 0.49, nearly 50%, right? The movement along x direction, ux direction, 49. So the range is here 48 to 49, 0.049 in the x direction. If you see in the 3D view, you can see here the x direction. So the color is showing you the displacements. The color is showing you the displacements. So you can see there is no displacement in the other direction, no displacement in the y or z direction. If you see the second mode, you can check here also in this arrow, it will show you the second mode. Just wait for it. Apply. There must be a glitch. I think I should uninstall and reinstall the software. Next class I will do it. Turn on and hit here. Yeah. Modal 2 and apply. Now you can see the mode 2 is moving along y direction. And if you see the third mode, let me click here. Let's see if it is working. Yeah. Now the third mode is showing you, see, the rotation. That means now this thing is the main thing that I should explain you. Here you can see we are getting the rotation. This midpoint, if the structure is rotating like this, so this is the center. If your center of mass is at this midpoint, this is the center. So this center, and it is moving like this along this direction, right? So there is no movement of the center. There should not be any movement of the center, right? If it is a proper circular motion. Okay, if it is a proper circular motion, there should not be a movement in the center, but the other corners or the other periphery parts should be moved. And you can see whatever displacement we are getting, it is at the outer part. When you are going far away from the center, the displacement is increasing here. When you are coming nearer to the center, here the displacement is very minimum, which is 0, you can say. Okay, tends to 0. There are displacements, but very less as compared to the other parts. If you see the contour here, you can see the range of the displacement. Here is 6.0 power e power minus 3, and here we have the displacement, which is I think the range of 72 to 78. It is showing here in the x direction, which is 0.062. So in the range of this one, 60 to 66. So you can understand that contour is giving you the values, or to understand the displacement, which part of the building is displacing at what amount and along which direction. The shape is telling you the direction and the color is telling you the value. You can check the value by going here also. Even without going there, you can understand from this contour. Okay, so this contour will help you to correct your rotational modes. If we have any rotational mode in the structure in the first mode itself, this contour will tell you which part of the structure is not moving. Here we can see clearly said this center of the part is not moving. Okay, because this is the center. So if this center is here, suppose this center is not at this position, but this position, this particular position. Now what will happen if it is here? This part is not moving and the other part is moving. That means you will get a rotational motion like this. In the third mode it is okay, but in the first mode if you get like this, it is not a actual or ideal behavior, right? So to understand which part is not moving, that means which part is more stiff, and which part is moving, that means which part is less stiff. Now this difference between the center of mass, center of rigidity, static eccentricity, design eccentricity, I will explain in the accidental torsion part. Okay, this is called accidental torsion actually. I will explain it in the later part. But yeah, I can show you the animation also. Let me show you the animation for the third mode. Let's go to the 3D view so that you can visualize how it is moving. Let's turn on the animation. See, this is not under any lateral. This is just the free vibration of the damping. How it is visualized. We have second mode. If you run the animation, you can see it will be moving along y direction. Each diaphragm is useful for mathematical model. In actual case, we can assign shell thin. Yeah, shell thin. Okay, there is a problem. Let me save it again. I think I have to. Yeah, shell thin. You have to assign, no doubt, for taking the slab, the behavior of the slab. But diaphragm is important in ETABS, because if you do not define diaphragm, it will not take a proper behavior of the diaphragm or proper load transfer mechanism. In other models, in other softwares like StatPro, in StatPro, if you model the plate, that plate itself is the semi-rigid diaphragm, and if you do not model plate, then you have to assign the master node, or in the latest version you have the rigid diaphragm option. So different softwares have different philosophies, different working methodology. So in ETABS, this is what you have to define by yourself, okay, whether it is rigid or check happened. I think things running. Just give me 1 second. I'm really sorry. Actually, software is having some issue. Yeah, let me take some questions if you have any question till now regarding the thing I have explained now. Should work now. Sorry. I do not have the ex E2K file also. Otherwise, I could have opened this file in the ETABS 2016 version. I have the 16. Just let me check the issue. Service is running somewhere. Okay, I think we can't continue today because software is having some issue now. If I make a restart, it will work actually. Yeah, it is working. So yeah, now let me open the model again. Okay, so let's see the second mode. If you see the second mode, let me analyze it. I think it is not saved. Having an issue today. I don't know why. Yeah, Mahesh, I'll actually explain if the first mode is rotational, what we should do in a different model, because in this model, as we have a proper distribution of stiffness and mass, we're not getting that issue here. But I'll take a different project in our next lessons, and I'll show you what we can do and how we can solve this issue. Okay, not an problem. So let me just show you the second mode. If you go to the mode 1, second mode, apply. Why it is not working? There must be a third party software which is running behind it, which is creating this issue actually. I'm sure alt drag is running behind somewhere, capable of finding. This is an issue. Okay, let me check whether it is working. Otherwise, I'll finish the live now, and in our next lesson, we'll see how to check all these things, because I need to fix it out. Yeah, actually, there is an issue with the software. I need to check it out, and I'll try to solve it and before our next class. Okay. So yeah, today we have seen how we should do the modal analysis. I thought of going further with the definition of earthquake load and wind load, but as I am having some issue with the software, I'm really sorry that I think I should finish it here, because I'm not able to continue actually. I need to reinstall the software. Okay, so thank you all of you for being with me in this session. Really, I'm really thankful. I hope in the next lessons also I'll see you. I'll have you in my classes. Okay. Yeah, Bishal. Yeah, tell me. Yes, I think there is an issue with the software itself. I was using a alt drag software for some reason. That software is doing some glitches here. I'm not able to fix it. I need to restart the computer and it will be fixed. Okay, Siddiqui sir, I'll try to install 19.1. I think that to change this version. Okay, let me take some questions. If you guys have any question or any query regarding up to this, we have what we have done. We have modeled the structure. We have provided. We have given the gravity loads. We have given the diaphragms, right? And we have defined the modal case. We have defined the mass source, and we have checked the modal analysis also. But the modal analysis that we have checked is the very simple, because this structure is very simple. But in some cases where you can get rotation in the first mode itself, this is the actual problem, that if you are getting a rotational mode in the first mode itself, how you should, or how you gonna solve this issue. This is actually I wanted to explain, but unfortunately in this structure this phenomena is not happening. So I'll try to take a different structure in our further lessons. I'll try to explain you how you can actually make changes in the orientation of the column, how we can distribute the stiffness, and how can distribute the mass. It is not possible to distribute the mass. We have already defined the loads, right? So the only thing we can do, we can distribute the stiffness accordingly. So I think yeah, I'm not gonna continue today. Yeah, this session will be upload, Mr. Avinash. This session will be uploaded. All the sessions are there in my channel. Share the AutoCAD file in the Telegram channel. Okay, if you are okay, all of you, I'm just requesting all of you, please join the Telegram channel that I have created. I have already provided the link also in my. If you go to the about page in my channel, or the posts that I'm giving in the YouTube, you can go there and you can check it out. The link of the Telegram channel. Join this, and I'll be providing all the materials there. So, what is the use of reference load? Yeah, reference loads is in the concept of Stat Pro, Mr. I couldn't. Yeah, Lakshmi Vashant Varun. Yeah, Mr. Lakshmi Vashant Varun. I don't know. The use of. I'm really sorry. I am not able to pronounce your name properly. Really sorry, Lakshmi Vashant Varun. Yeah. So the use of reference load case is it is the concept of Stat Pro. The thing that mass source is doing here in ETABS, that means the seismic mass, the same thing the reference load is doing there in the Stat Pro. Okay, in Stat Pro there are different methods to define the seismic mass. Okay, there are different methods. You can create the seismic mass separately also, but the reference load is the easiest way, that again and again you don't have to assign the loads again, like create the load cases as a mass, seismic mass, and you can again assign it to the corresponding members. So rather doing that, you can create a reference load, okay, taking the loads which you have assigned already in the structure, and that reference load can be used in the seismic definition in Stat Pro actually. So as I have told, every particular software has their own philosophy to actually solve the issues or solve the problems, right? So ETFs works in a way, or all the CSI softwares actually works in one way or one particular way actually. The Bentley softwares have different methodology. If you go to with Strap, I'm working with Strap for actually now. Strap as foundation. These softwares I'm working with nowadays, and they have their different methodology or this different philosophy to solve the problem. Okay, I'll try to explain actually. So I think so. What is, yeah? Is there any other query? So what type of checks we do after analysis? Today we do model, not model actually, Mahesh. It is modal analysis, mood shapes. Okay, there are stability checks. Okay, means a drift, displacement, and there are irregularity checks, geometric irregularity. There are torsional irregularity, stiffness irregularity, which is also called as soft story effect. Yes, Mr. Singh, I'll try to continue the class in this week only, because the internet condition is quite stable from today, and I hope it will be stable in coming days also. I don't know why I'm getting this problem with the software today. I'll try to reinstall it and I'll continue. Maybe tomorrow it's not possible. Maybe day after tomorrow or okay. I'll try to keep it day after tomorrow only. Let's see. Is there any question? Any more question? Yeah, Mahesh, what I'm saying, like there are different checks, stability checks, irregularity checks. Okay, then in the modal check is the very important check. Okay, if your modes are not correct, if you go with the dynamic analysis, you will get a very wrong values, because the response spectrum totally depending on the mode shapes. Okay, it used to make combination taking the mode shapes itself. Yeah, so Mr. Singh is saying, sir, if 90% of is not coming out of number of modes 5, but if we get after 12, then is it? Yes. Whenever you are getting, see, you have one idea, right? At, suppose our structure is just G plus 2. So in that case, the mass participation should be in the 10 to 12 modes. Okay. But in case of high rate structures, it may go for 30 modes, 40 modes also. Okay, no, you cannot actually say that it will be restricted to 12 modes or 5 modes. Okay, but you should have a basic idea that our structure is that much height, or the behavior should be like this. As I have explained, the degree of freedom of the total structure and the levels, you can calculate like this also. So now if the number is exceeding, that means, and if you are not getting mass participation even after increasing the load cases also, that means there is a problem in the model. So to solve this, you can check the model again, and if you cannot find any problem in the model, there might be a small part of a beam which is extended, a small node which you have left, then you can go with Ritz analysis. Okay, Ritz vector analysis, and it will solve the issue. Okay, and whenever you are, if you are not getting 90% in the 12 mode, you have to unlock the structure, you have to go to load cases again and increase the number of modes to 15, check it out again. If it is not increasing, then again increase 3 or 5 more, and at least 90% mass participation in both planned directions you should have. Is there yeah. See, all types of checks I'll do in this structure. First of all, as I have taken this structure, I will complete this structure up to design, and after that I'll take another model, another suppose the irregular shape. Mahesh, I'm telling you, I'll take another model and I'll check the same things, but there will be, the problem will be different, right? As we have, if you take a regular structure, the problems will be different. So we'll try to solve those problems in that model. But for now, as we have taken this model, we'll first complete this. Otherwise, it will be a mess. We have taken another model, irregular shape, high rise, then it will be a total mess. So it is better to complete one, and after that go for the next one. So any question, any other question? So I think, yeah, this is it for today. I should not extend it as my software is not working so far, so it is better to finish it here. All of you be safe, stay at home. The situation is really very bad, really very bad. So it is better to stay at home. Whoever is working, please take proper precaution while going out, and especially who are the diabetic patients. Now the black fungus is there. It is going to, I don't know how many new problems or new diseases are going to create. This COVID is going to create how many new diseases in India? I do not know. Yeah, all of you be safe, um, take precautions, and stay at home. Okay, it is better. Thank you all of you for joining for today. Good night.